Regression is a similar but related tool compared to Pearson's R. Now with Pearson's R, there is a best fit line generated, and then we measured the consistency of the relationship. So Pearson's R gave us a good idea of how consistent that relationship is. And is generalizable to regression as well, and it's a very important part of regression. So let me take a moment to kind of transition from Pearson's R into regression and explain how that consistency matters. So in the diagram here, we see a few things. One, we see our best fit line, which is the diagonal line. However, then we see the mean of y. And so the reason the mean is used here is because if we knew nothing at all about what value y should be, the best overall guess would be the mean. And that's why we have the mean, right? It's a summary value that hopefully best describes the distribution in terms of its center. So if we knew nothing about y at all, the mean would be the best guess. But the best fit line tells us based on x, this is where y should be. And so that's where the point y subscript p, that's the predicted value of y, that's our next best guess. Rather than the mean, we prefer to use the predicted value of y. This is where y should be if x is this value rather than just the mean. The distance between the predicted value and the mean is what we refer to as explained variance. Then there's the actual value of y. In this instance on the diagram, just y, right? It's the actual point. So when you have long distances between the predicted value, which is on the best fit line, and the actual value, you have an inconsistent relationship. But when you have short distances between the predicted value and the actual value, you have good consistency. In this instance, that distance is called the unexplained variance. And we want the regression line to be as accurate as possible. So therefore, we want very small unexplained levels of variance and prefer to have larger, relatively speaking, explained variances. So the ratio of explained to unexplained variance is what gives us our R-square values. The larger the explained compared to the unexplained, the larger the R-square value is. And so that's what we want. To have a strong relationship, we need to have very short distances between the predicted value and the actual value, right? That's the line of best fit. So that's the inconsistency or the consistency if those values fall on or near the line. So that helps us figure out how strong the relationship is in terms of regression. Regression adds a piece of information that Pearson's R doesn't necessarily take into account, and that's the actual slope of the line. Pearson's R ignores the slope. All it cares about is measuring the consistency of those points. The slope of the line tells us how much change in x, which is a 1 unit change in x, will result in a change in y. And so if you have a very steep slope, you can get very small changes in x, yielding much larger changes in y. However, if you have a flat line or a very low angle line, small changes in x, one change in x, a 1 unit change in x, will lead to a very small change in y. And so you can have a perfectly consistent correlation, right? Meaning all the points fall on a predicted place as they should. However, if that line is relatively flat or almost or slightly above being flat, the effect of that relationship is very small, meaning you have to do a whole lot of that changes in x to get a substantial increase or change in y. So if you're trying to reduce the amount of crime and the line is very flat as opposed to a very steep downward slope, right, you have to do a whole lot of changes in x to reduce the amount of crime. Whereas if it were a steep slope, you'd have to change x only a small bit to get big reductions in crime. So the flatter the line, the more effort and energy and time and resources you have to put into it. The steeper the line, the less effort you have to put into changing y, or to get the result that you want in that reduction in crime. So in other words, programs in the example above, programs work, but its effect is very small when the slope is fairly flat. But when you have a steep slope, you can have small changes in your independent variable and have great changes in your outcome. Here's the regression formula. So y equals a plus bx, where a is the intercept when x is 0. And so that's a constant or a fixed point. So in this example, the intercept is 475, and that it is what it is and it can't be changed. Whereas b is the slope of the relationship between x and y. And y, you just insert whatever value you want it to be for x, to solve for x to get y. So in this case, we're measuring crimes over a longitudinal time period, and we have a relationship between yearly changes and how much crime there should be. And so to solve for how much crimes there should have been in 2010, we just use the formula and substitute our known values. 475 goes in for A. The slope was measured at 325, so that's substituted for B. And now we insert the year that we want. So in this instance, we can insert 2010, or we could go 2009, 2011. But once we insert that 2010, we multiply it by 325, and then add 475 to that, and we get 653,725. So that was the predicted number of crimes in 2010 for a particular place. So that's how you use the regression formula to predict what y should be based on an x value. So here our x value is the year, whereas the slope and the the slope and the a are known. So here we're using the x value to determine what the y value is, having already known what the constant is and what the slope is. So therefore we can predict what y should be based on the x value and the other two knowns. So this is an example of how slopes matter. So the first slope you see is a 1-for-1. So a 1 unit change in x leads to a 1 unit change in y. So this is a 45-degree angle slope. The next slope down is a slope that's greater than 1. So a 1 unit change in x will lead to a very much bigger change in y than 1. And so this is a big effect. So a small change in x will lead to a much larger change in y, whereas the line at the bottom is fairly flat. And so you need big changes in x to lead to very small changes in y. And so this is an inefficient or ineffective way to yield change in whatever your outcome is. And so this is a fairly flat line. When we examine the regression coefficient or a regression, we're concerned with the b value. And these are expressed in terms of the original units. Age is measured in scales of years, and proportion of young people in a city is measured in scale of, say, 0 to 1. The two units are not the same. And so to compare across different variables or to make it understood, we use what we call a beta coefficient. This is the standardized regression coefficient. And so it's a corresponding value to the slope of the line. So the slope of the line is a raw score. And the standardized regression coefficient is interpreted the same way no matter what variables you use. So it's in terms of standard deviations. So when you see whatever value for a beta you see, a 1 standard deviation change in the x variable leads to this value in the dependent or the y value. And so that's one way to have a standardized regression coefficient make sense. So we can compare predictors or other independent variables against one another and determine how large of an effect it has in terms of standard deviations in changing the dependent variable. So it's a useful coefficient or value to compare one variable against another in terms of how effective it is in changing the dependent variable. So because a regression relies on both consistency and slope, we can use beta or b to determine the effect. We can also use r to determine the consistency. So small r square values suggest that b is not a reliable, so you may have a large effect, right? The slope may be large, but it's not reliable if R square is small. However, if you have a large R square, which means you have a large Pearson's R, it suggests that the B value, whether it's large, medium, or small, whether that slope, no matter the size, is reliable or much more reliable than if the R square value is small. To properly interpret any linear relationship, specifically with the regression, you need both Pearson's R and the slope, or you can use the beta if you prefer. Like any test, multiple regression has assumptions that must be met, otherwise the results may be inaccurate or error prone. So all of the assumptions from Pearson's R carry over to regression, whether it's a simple regression involving an independent and dependent variable, or whether it's a multiple regression that involves many independent predictors. So you must have a straight line relationship between the IV and the DV. You want a normal distribution among the sampling distributions, and so it helps when your predictors are normal, but they don't always have to be, but it helps when they are. So you want to assess for that, and you want homoscedasticity, right? That's when the level of variance of the dependent variable is equal across all levels of the independent variable. Multiple regression has other assumptions that must be met. For instance, the residuals or the unexplained variance, that distance between the actual data point or the predicted data point for y, having a normal distribution for the residuals suggests that there's no systematic reason why those residuals aren't there, and we don't want that. We want it to be because of randomness, not because of systematic interference by some other process or variable. Additionally, the predictor variables, if there's more than one, so this wouldn't happen with a simple regression that just looks at an IV and a DV, but if you have multiple predictors, like multiple independent variables or control variables, you don't want those variables to be highly correlated with one another. If they are, this results in a situation referred to as multicollinearity, and it introduces inflated outcomes into the regression equation, and it will appear stronger than it is. And so we assess multicollinearity by looking at how highly the predictors and control variables are correlated with one another. Pearson's R is said to be a robust test, but even if all the assumptions aren't met, you can introduce error into the results. And so they are stringent, and if you violate them, that can happen. So we do our best to assess whether there is a straight line relationship and not a curvilinear relationship between the IV and the DV. And if there's only a small violation, you can be confident that the result is probably close to what it would have been without that error. But as the errors increase, if you don't meet all the assumptions, or if they aren't met by a small margin as opposed to a large margin, right, you can count on greater error being present in the results. So R is robust, but you want to make sure you're meeting the assumptions as best as possible. Otherwise, the error will be great. So our goal is to reduce the amount of error so that we have confidence in our results. Pearson's R and regression are easily generalized to multivariate level. So when we start beginning to introduce multiple variables as multiple predictors of an outcome, that's an ideal situation. We know that there are multiple reasons why things occur. It's not just because of one thing, but it's because of multiple explanations, multiple things lined up in a particular way, in a particular fashion, that led to this particular outcome. And so we try to capture as many variables that explain the outcome as possible, and usually that's more than one. And so multiple regression is easily extended to many more than one variables. Same thing goes for R. We'll look at semi-partial and partial correlations later. We can begin to incorporate many other variables into our assessment of relationships that allow us to determine whether this is a true relationship between the independent and dependent variable, and if so, if it is significant still, how strong is it? Did it change from the bivariate relationship, or is it still consistent, or is it even greater? And so that's why these things are important to us, so that we begin to examine the outcome as part of a multiple explanation process as to why it occurs.